class. Okay, so we're going to talk about the specific heat of a gas. And kind of left this board from previous videos. I did change one thing here. Earlier I'd written 3/2 capital N times Boltzmann's constant times the temperature. But for what we're doing now, you can see that big N times K is equal to little n times R. So I just changed these because they will be more useful for what we're doing now. But let's go back to what we did. Let's forget these pictures for a moment. I'll explain those in a minute. But let's go back to what we did before for the specific heat of a solid. So if you add heat to an object, you're going to change the temperature, provided you're not causing a phase change to occur. And the more the heat you add is directly proportional to the change in temperature, or really the temperature change is proportional to the amount of heat added, and inversely proportional to the mass. So we put it together, looks like this. This is not a convenient form for talking about gas, though, because if you look at this equation, M is just a measure of how much of that substance there is. Now, for our purposes, the amount of substance, if we're talking about a gas, is better described by just like the number of moles. So we're going to write for a gas, so this is for solid or liquid. We're basically going to write it like this, where instead of mass, we're going to talk about the number of moles. Simple, trivial change. Guess we're done here. No, it's a little more complicated than this, though. Because what I've drawn two different pictures here. This picture, we have, say, a cylinder that is just filled with gas. I don't know if you can see these dots. I don't know if they're showing up on, well, whatever. It's filled with a gas. And let's say we add a certain amount of heat. Let's say 1,000 joules. The temperature of this gas is going to rise. Now, what if we add 1,000 joules of gas to this cylinder? Now, the difference here is that this cylinder, we have a movable piston here. So if we add the heat to that gas, what's it going to do? It's going to expand. The pressure is going to increase when you add heat to it, and so it's going to expand, and it's going to be doing work on its environment. Like we could have a mass up here, and if we add heat, that's going to lift up this mass, and it's doing work. And as a result of that, this gas is going to lose some of that energy you're adding to it. Like if you add 1,000 joules to the gas, maybe 500 of that is going to go into lifting the mass. And so only 500 joules is going to go into changing the temperature. And so we're going to get different temperature changes in these two cases. So like the details of what's going on to the gas when you're adding heat to it, they can have a significant difference on what is going on inside the gas. So we're going to look at kind of two cases. I'm going to erase these pictures. That's just to kind of illustrate the idea. I'll write down our equation. Okay, so that's what we use for a gas. However, we're going to look at two particular, I'll make sure this is all visible. Yeah, it's unfortunate. Like what I can see on the screen is a little smaller than what shows up in the video for some reason. So it's hard to tell exactly where the cutoff is. But anyways, yeah, we're going to look at two particular processes where we add heat and look at the temperature change. And to start out with, we're going to look at an isovolumetric process. Actually, I'm going to write something else first. First, we're only going to consider a monatomic gas. And what we're going to do now is we're going to look at an isovolumetric. Which, if you remember, that means constant volume. So that's like that rigid cylinder. So basically, all the heat you're adding, that's all going to go into raising the temperature of the gas. Okay, and so to kind of signify we're talking about this process, we're going to say Q so C is the specific heat of the gas, but remember, we can't really just say a gas has a specific heat because it depends on, what the gas is doing while you're adding heat to it. So we say this is the CV. That means a specific heat for a process that is being carried out at a constant volume. So Q equals Cn delta T. All right, so this is for an isovolumetric process. That's when we use that one. And if the volume is not changing, in this case, we can say that the work being done by the gas is 0. If the volume isn't changing, it can't really be expanding and pushing on things. I guess we'd have to be a little more precise. You could have a container where the dimensions change while still keeping the volume constant. So it could be doing work on its environment and the work is being done by the environment on the gas simultaneously, but the net result is going to be 0. The net work done by this gas is 0. So remember the first law of thermodynamics. So remember the internal energy of a gas only depends on the temperature. Well, it also depends on the amount of gas and the type, but for any given gas, the internal energy depends on the temperature. And the first law of thermodynamics says that the change in energy is Q plus W, where Q is the heat exchange. In particular, Q is the heat that is added to the gas. So heat can go either way. So in this equation, say Q is positive when heat is flowing into the gas. And again, you don't have to memorize that convention. Just think, if energy is flowing into the gas, if Q is positive, then according to that equation, the internal energy is increasing, so we know heat is flowing in. Heat is just a form of energy. And so it's entering the gas, it's increasing the energy of the gas. Now, W is the work that is being done on the gas. So if work is being done on the gas, that's causing the energy of the gas to increase. So in that example with that expanding piston, the work would be negative in that case because we added heat and the gas expanded doing work, and so in that case W would be negative. All right, well, if W is 0, then Q is just equal to the change in internal energy. So, Q plus W is the change in internal energy. And remember, we're dealing with a monatomic gas here. So, I'll write this off to the side and erase it. I think I'll just do this once. say we have E is 3/2 nRT. Delta E, I'm going to work through the algebra just one time. Very easy to bypass this algebra. But the change in energy, that'd be like the final minus the initial. So we'd have 3/2 nRT final minus 3/2 nRT initial. And we can factor out this 3/2 nR. And this T final minus T initial is delta T. So basically, from now on, we're just going to, when we have two variables, and one is just like this 3/2 nR is a constant. So if one variable is just a constant times the other, we can say delta E is 3/2 nR delta T. So Q is delta E. This would be 3/2 nR delta T. So that's what we have there. Okay. Now, remember from our let's compare this to our definition. I'm just going to rewrite this. 3/2 R times n delta T. And just from comparison, we can see that CV is equal to 3/2 R. Now I have to decide what, I think I'm going to rewrite our equation board on the right and just keep what we need for this particular lecture. So, I should have probably just done this from the beginning. So yeah, for monatomic and diatomic gases, just to note, these values are actually going to change later on. But for now, we're going to go with them. And then we have the first law. And then we have Q is Cn delta T. All right. So what we have now, we're going to make a table over here. So we're looking at a monatomic gas and finding CV, that is 3/2 R. Okay. So we're done for a monatomic gas looking at this isovolumetric process. So now what I want to do is look at an isobaric process. Okay, so an isobaric process, that's, remember isobaric, barometer, think pressure. This is constant pressure. And remember the work, in this case, is minus P dV. Or, let's just call it delta V. I mean, it's, yeah, for an infinitesimal amount of work, that'd be P dV. But again, because P is constant, if we integrate it, the integral of dV is just delta V. So for an isobaric process, we can write this down. Work is minus P delta V. And now, actually, yeah, I'll write this here. The, Q is Cn delta T. In this case, we'd write this specific heat as Cp for constant pressure. So Q is Cpn delta T. So now let's look at this change in internal energy. Let's look at the first law of thermodynamics. So delta E internal, we're dealing with a monatomic gas. So we'd have 3/2 nR delta T. That's delta E. And that is equal to Q plus work, which is minus P delta V. Okay, so this is just the first law of thermodynamics. Delta E, that's this term. This is Q. And that is the work term. Now, we're dealing with an ideal gas. So we can say PV is nRT. And remember, P is constant in this case. And so basically, well, N and R are also constant. So the only two equations, the only two variables we have are V and T. So we can say P delta V is nR delta T. So let's plug that in. Yeah, just this equation, this P delta V, we can throw that in here. So here, that's like off to the side. So we have 3/2 nR delta T minus nR delta T. Now we can factor out the n. Each term has an n delta T. So we can just factor those out and get rid of them. And we're assuming there's a temperature change, so delta T is not 0. So let's get rid of those. So what we have is 3/2 R equals Cp minus R. So if we just get rid of n delta T from each term, here we have 3/2 R. Here, getting rid of the n delta T just leaves Cp. And getting rid of n delta T here is just R. And 3/2 R, that's Cv. Or we could kind of rewrite this. I'm going to write this over on our board on the right. I left a little room up here. But we have this very important result. Cp minus Cv equals R. And so, yeah, if we wanted to solve for Cp, that'd be Cv plus R. So we'd have 3/2 R plus R. That would be 5/2 R. You know, I'm gonna erase this table because it's not in the right place. You can always write it down later if we need it. One more thing I'll write down the results we have though. Cv is, here, this is for a monatomic gas. So yeah, CV, the specific heat at constant volume, is 3/2 R. And at constant pressure, that's 5/2 R. And again, this is consistent with what I mentioned earlier, that when you have like that rigid container, all the heat you're adding to it is going to go into a temperature change. So we should expect a relatively high temperature change for the constant volume case and a lower temperature change for the constant pressure case. And that's what we get. Because, like say we had a certain amount of heat. So if C is smaller, delta T has to be larger. Conversely, if C is larger, delta T is going to be smaller. Now, there's one more thing that's going to be very important. We're going to define this number gamma as the ratio of specific heats. So gamma is Cp over Cv. So for a monatomic gas, that's 5/2 over 3/2. So gamma for a monatomic gas, according to what we've been doing here, is 5/3. I have a I have a table here. It didn't turn out too well. But 5/3, that's 1 2/3. So that's 1.67. And I printed out 2 of these. They didn't come out too well. But let's see if this is visible at all. This isn't just, I literally took this straight from the book. But this, it's not visible. I'm going to write down some of it. But we have various gases: helium, argon, neon, and krypton. Those are all monatomic gases. So I was hoping holding up that table would work, but it did not. So I'm going to write down some values. So everything we've done right now was for a monatomic gas. So let me just erase this, and then I'll write down some of this table. Cp and Cv, I don't want to write those down. But yeah, we can calculate these as numbers. Remember R, I'll just write it here. That's 8.31 joules per mole Kelvin. That's the universal gas constant. And so Cv should be 3/2 R. So that should be about, what, 12.5 roughly. And just multiply this. Half of 8.3 is 4.15. So if we add that to it, we get 12.5 roughly, if we round off. So yeah, Cv for all these gases, we're looking at helium, argon, neon, and krypton. I'll just read off the numbers: 12.5, 12.5, 12.7, 12.3. That's pretty good agreement. These are experimentally determined numbers for the specific heat. Now Cp, that's 5/2 R. So just multiply that by 2.5. I'll just do 8.3 times 2.5. Should be around, okay, I tried to do this a little too quickly. $30.8, 20.8, sorry. yeah, roughly 20.8 is what we derived that result. And yeah, if you look at that table in the book, for CP, for every one of those gases, it's 20.8. And now gamma, for all these gases, I'm going to read off these numbers: 1.67, 1.67, 1.64, and 1.69. So we have very good agreement with what we're deriving, based on like the equipartition theorem and first law and all this fun stuff, and these experimental results from actual gases. Okay, now let's look at a diatomic gas. Now it's actually going to go a little quicker. I'm going to write this off to the side, kind of running out of room on that board. But let's look at an infinitesimal change. Oh, wait, sorry. I'm going to write let's stick with this isobaric, isovolumetric for a moment. So in that case, the change in internal energy is just Q. Okay, so again, this equation is valid because we're using CV. So if it's an isovolumetric process, then W is 0. And yeah, let's solve for CV. And we can write this as a derivative by looking at an infinitesimal change. I wish I could write it on this board over here, but I didn't really leave myself any room. But in general, CV is going to be 1 over n times the derivative of the internal energy over the temperature. So this is going to be our strategy. We're going to look at a diatomic gas. And our strategy, here we have CV, and then CP is just going to be CV plus R. So we can find both specific heats by just looking at the energy and taking a derivative. Fairly simple process. Now, what we had before, remember for a diatomic gas, we look at translations. We have 3 degrees of freedom. For rotations, for a diatomic gas, there's going to be 2 degrees of freedom. And then vibrations. We would expect 2 more degrees of freedom. Like the molecules the atoms are moving back and forth. There's that electrical potential energy, which is quadratic, like a spring force. And the movement of the individual atoms have kinetic energy. So that'd be another degree of freedom. So what we should expect here is the internal energy for a diatomic gas should be 7/2 nRT. Now let's calculate our specific heats in this case. Very easy now using these formulas. So CV, so 1 over n, we'll just cancel out that n. And again, 7/2 and R are constant. So when we take the derivative of this, we're going to get 7/2 r. So basically, yeah, the n is canceled out by the 1 over n here. And we're taking the derivative. So the derivative of t with respect to t is 1. So we're left with 7/2 r. And Cp would then just be 1 more than that. We just add r, so that should be 9/2 r. And then gamma, that's Cp over Cv, that's 9 over 7, which is about 1.28. Let's look at these values. 3.5 times r So this is going to be around 29.1 joules per mole Kelvin. And then 9/2 r, well, we can just add r to this. Let's say around 37.4. Okay, so these are the values that we're coming up with based on our analysis, what we should get for a diatomic gas. Cv should be around 29.1, Cp is 37.4, and gamma should be around 1.28. So let's see what we get. 29.1, yeah, I can't even read this too well, but for Cv, I think it's 20.4. Oh, we're looking at helium, nitrogen, oxygen, carbon monoxide, and chlorine gases. So I'm going to read these values for Cv. We should be getting 29.1. What we're getting is 20.4, 20.8, 21.1, 21.0, I think, that one's hard to read, and 23.7. Those are a bit off. And then for Cp, we're getting, we should get 37.4. What we're getting is around 28.8, 29.1, 29.4, 29.3, 34.7. Looks like our Cp values are actually closer to these Cv values. And then gamma, which would be around 1.28. The experimental results are like 1.41, 1.40, 1.40, 1.35. Bit off as well. So it looks like our model did not do all that great in explaining what's going on for a diatomic gas. It worked really well for a monatomic gas, not quite as well when we're looking at a diatomic gas. And there is a reason for that. But one thing you might have noticed is that, if we're looking at all these gases, these diatomic gases, the Cv values were actually close to this. And we can think of it, maybe these gases, for some reason, only have 7 degrees of freedom instead of 9. So, what we got for, Cp has that kind of 2 higher than this. So, again, if a diatomic gas only had 5 degrees of freedom, that would actually give us some that would actually make sense. It looks like this diatomic gas, based on the experimental results, would only have 5 degrees of freedom. So what's actually going on here? And there's a reason these results are off, and that reason is quantum mechanics. Like, we kind of just assumed that this diatomic gas has all of these degrees of freedom, which classically is a very good assumption. Things can move, so we shouldn't have a problem with these translational degrees of freedom. We know that these gases are going to be moving around. These molecules are going to move. They're going to have 3 degrees of freedom. And what about these rotations? And again, we haven't really studied quantum mechanics, but the name itself kind of might give you an idea. Yeah, I'm not sure what everyone's background is, but basically, quantized. Everything has kind of discrete values. Like you are probably aware, if you look at an atom, you have a nucleus which is positively charged, and this very crude picture where you look at an electron as a particle that orbits the atom. That's kind of an older picture. But this is called the planetary model of the atom. It kind of looks like, you know, if you have multiple electrons, you can think of it, they're orbiting, just like different planets have different orbits about the sun. But there's a very big difference between, this planetary model and our solar system, and that is that for a given nucleus, there are only certain orbits that are allowed. Like an electron can exist in a stable way right here, or it could exist here, but it cannot exist in a stable form like anywhere in between. You won't get an electron that's just hanging around in between these 2 orbits. Now you might think, well, that looks just like our sun and the planet system, except it's not. Like if we wanted to, we could build a spaceship and put it in orbit between Earth and Mars. There's no reason something can't orbit in between Earth and Mars. Just nothing happens to, well, there's asteroids, I guess, but yeah, you can have an orbit any distance from the sun. I guess if it's too far away, it could get carried off. But there's only certain, like, discrete values that are allowed in quantum mechanics. And the same applies to rotations. Like energy also comes in discrete pieces. And so when you talk about a rotation, it has to have a certain minimum amount of energy to be able to rotate at all. And similarly with vibrations, there's like a minimum vibrational energy. If you're below that, your molecule is not going to vibrate. And so there's a nice picture from the book, which unfortunately my printer is pretty horrible. But again, if you have the book, this was taken directly out of it. I think this is for helium gas, which is diatomic. I said helium, which is monatomic. This is hydrogen. And we're looking at the internal energy as a function of temperature. And at low temperatures, we've got that 3/2 R. Or we're looking at the specific heat, which is related to it. But at low temperatures, this diatomic molecule is acting like a monatomic atom. It only has translational degrees of freedom below here. But then as the temperature warms up, the molecule can start rotating, and the specific heat jumps up to 5/2 R. And then at higher temperatures still, then you can have vibrations contributing to the energy. And so the specific heat depends on what types of energy are available, and that depends on the temperature. So I mentioned earlier these numbers are going to change. Well, for a monatomic gas, we're fine, but for a diatomic gas, typically at room temperatures, we'll have translations and rotations. So this number at room temperature should actually be 5/2. So kind of classically, we should expect some of the energy to show up in terms of vibrations in the molecule, but that does not happen at room temperature. There's not enough energy to cause these vibrations. And now, so again, this is at room temperature. If we cool the gas down, this diatomic value is going to drop to 3/2. Or if we heat the gas up to very high temperatures, we're going to jump up to 7/2. And so, yeah, it depends on just what types of energy are available, and that depends on the temperature. And again, this was like a major failure of classical mechanics. You know, we predict certain things, and then we do experiments, and it doesn't match up. And typically, when you have a very successful, you know, theory, and then you do experiments and it doesn't quite work out, you kind of think, okay, we're missing something. You know, the fundamental theory is okay. You know, we're just not taking something into account, which is why our results are not what we're expecting. But no, this is one of those cases where the theory is fundamentally wrong in this case. Classical mechanics breaks down. So like this behavior we're seeing in this picture, this is explained by quantum mechanics. And that historically they did not develop quantum mechanics based on this. It was based more on the energy levels in an atom, but that was kind of an early success of quantum mechanics, is explaining these like gamma values for gases in a way that matches with the experiments. So the specific heat of a gas, it depends on whether it's monatomic or diatomic, and it can also depend on the temperature. And more complicated molecules would have more degrees of freedom. We're not going to get too involved with that. We're just going to focus on monatomic and diatomic molecules. Or I guess monatomic, just atoms, and diatomic molecules. All right, so that will be it for this video.